to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we are dusting off our astrolabes, polishing our parallax, and consulting the heavens, because our next subject quite literally mapped the stars. I used to have a job driving an ice cream van. But before I became a self-employed professional ice cream man, I was an ice cream boy, apprenticed to an old master of the trade. I thought it would be the simplest gig in the world. You drive, you play the tinny music, you hand out frozen treats, you get paid. Simple. On my first day, the owner, a man who I can only assume took me on as an apprentice because he was no longer allowed near children, handed me a set of keys and a map. Now, this wasn't a normal map. It was a laminated, gravy-stained relic, covered in annotations from the begrizzled old man who previously warmed my pleather chair. His route made no sense. It wasn't a neat, logical circuit of the town. Instead, it was a sprawling mess of circles within circles. The main route being a big loop down Rowlands Hill, round the Minster and up past the Horns pub and back to the depot near the cricket pitch. He labelled that the deferent. But branching off of it were dozens of smaller compulsory loops, with annotations like, at 3:15, an instruction would read, you must leave St John's Hill and do a lap of the Lye estate. Then at 4, turn off towards the Minster and circle Redcott's twice before continuing. I thought it was madness. I was a modern man with a smartphone. I could create a far more efficient route. Park Lane, East Street, West Street, Hannam Road, back past Waitrose, back to Park Lane. I could do the whole town in under 15 minutes. So on my second day, I ignored the boss's map, and I drove my logical, streamlined, efficient circuit. And I sold precisely 3 ice lollies, all to the same regretful-looking bride sitting outside the Dean's Court wedding venue. Dejected, I went back to my boss's Ptolemaic masterpiece the next day. I followed its bizarre instructions to the letter. At 3 o'clock, I dutifully pulled off Rowlands Hill and gently braked down the dangerously steep St John's, and then I saw it. The side gate of the first school opened, and a flood of children poured out, taking that exact route home. I was a hero. Later, at 3:45, I circled Churchill Road, when I heard the final whistle of the under-14s rugby practice. Oh, legend. Turned out, Boss's map wasn't designed to be geographically efficient. It was designed around a different centre of the universe, the predictable, observable orbits of children and tourists. Data. Each loop was an epicycle. It was a finely tuned calculation to place my van at the right place, at the right time, including sometimes if I had to go back on myself. The system was utterly bonkers if you looked at a street map, but it worked perfectly. It was helpfully, brilliantly, and profitably wrong. Today then, a big name on campus. Who's that? Claudius Ptolemy, or Ptolemy if you're a friend. Not to be confused with Ptolemy I Soter, the Alexander the Great's general turned pharaoh turned taxonomic nightmare. No, this is the Greco-Roman polymath whose work would guide the sciences of astronomy, geography, optics, and yes, mathematics for over 1,000 years. Now, if you've been following along, you'll know episodes of thinkers whose ideas orbited around rational thought. But today's guest didn't just orbit thought, he orbited everything, quite literally. He gave us a model where the Earth sat smugly at the centre of the universe, while everything else spun around it in a celestial game of who wore it best, retrograde motion edition. When applying ancient and modern rhetoric, there is a fallacy of appealing to an authority. And when it comes to making massive mistakes about centricity, Ptolemy is that authority. But Ptolemy was more than an astronomer. With a flair for circles, he was a calculator, a tabulator, a theoretician, and, whether he wanted to be or not, a future argument waiting to happen. Let's begin in Roman Egypt. Claudius Ptolemy lived and worked in Alexandria during the 2nd century CE, most likely between 100 and 170 CE. We don't know much about his personal life, but we do know that he wrote in Greek, bore a Roman name, and lived in Egypt, so let's just say he was a mathematician. Alexandria, at the time, was still a hotbed of learning. It had lost its famed library to a series of fires and unfortunate storage decisions, but the museum, a kind of ancient research institute, still attracted scholars. Ptolemy likely worked there, compiling, correcting, and expanding the work of his intellectual ancestors. His influences include Hipparchus, the observational genius who catalogued stars and puzzled over lunar motion, Menelaus of Alexandria, who wrote on spherical geometry, and Apollonius of Perga, the king of conic sections. Ptolemy inherited this tangled mess of circles, chords, and calculations and turned it into something people could actually use. The result? A treaty so influential it simply became the mathematical treaty. Later Arabic scholars, being the practical sort, called it Al-Magisti, the greatest. Europeans, they just mispronounced that as Almagest. This might be an opportunity to talk about pronunciation. I have, so far, dealt with many scholars from the Mediterranean basin. Generally, we call them the Greeks, but they did not call themselves that, nor were they a homogeneous group. No more than people that live in Italy, Greece, Turkey, Egypt, and the numerous other countries that border the Med are a single group today. So it's nice to take a moment and appreciate the diversity of the origins of maths. We could possibly call them the Hellenistic peoples, without being too far from the truth. As a lot of the people there spoke the Greek language, they might have emanated from colonies that started in Greece but then later took over other places, but there was quite a lot of assimilation going on as well, so we don't really know too much about who these people were. Given, however, that the language of these people is now dead, I have felt fairly safe in pronouncing the names in a way that is easy for my mouth to make the sounds. However, as we move through history, we are going to find a lot more Latin and a lot more Arabic, for which I will do my best. Now, I know what you're saying. Surely the Greek language is not dead. There's a whole country of people that speak Greek, and yes, there is, but there are some distinctions that we should make between modern Greek and the various different forms of ancient Greek that were spoken throughout the time. I think it's safe to say that we don't know for sure that I'm mispronouncing things, although, in fairness, I probably am. What I am cautious of, however, is the colonialisation of the history, by which I mean in late ancient and early Renaissance times, the historians of the day, for reasons of ignorance or most likely xenophobia, tried to steal the lineage of the ancient sources. Now you might notice there I said the historians, and you're probably thinking of the white European historians, but it's not exclusively a European thing to appropriate historic sources. However, when it comes to racism, we have form. Naturally, every culture wanted to draw a line from Aristotle or Plato or Cicero to themselves as the inheritors, or at least every culture that was around the Mediterranean basin. The Renaissance, after all, was all about picking up the pieces of the Roman Empire and pretending that nothing had changed. Naturally, in other parts of the world that we've not yet dealt with in this particular timeline of history, there were ancient sources that were just as coveted as a direct lineage, but we will come to those ones when I am more educated in them. In my own heritage, and that is as a European, our great authorities of maths and science are all written in Latin, which is fine. But that means that every work, and oftentimes the names, originally written in another language, get badly rearranged into a Latinization. For instance, the great philosopher Avicenna is actually Ibn Sina. Again, could be ignorance or malice. I don't know. Back to Ptolemy, I know that he didn't call it the Almagest. Instead, the Arabic translation is Al-Magisti, but I doubt he called it that either, given he didn't speak Arabic. As far as I can tell, the original Greek title was Mathematicae Syntaxis. So, with all of these episodes, I'd like you to know that I'm trying to present the history in a way that is both respectful, helpful, and if at all possible, correct. But these three priorities do not always align. For Ptolemy, I'll be calling it the Almagest, because that's what it's known as to me. And with a big thank you to the string of writers of the copies and the translations who kept it alive for centuries, largely in Arabic and then later on in Latin. So let's talk about the Almagest, Ptolemy's most significant astronomical text. It spans 13 books and is more exhaustive than a set of counterexamples for the largest number. In it, Ptolemy presents a model of the universe that will be used, copied, revered, and later violently refuted. Very violently. Here's the setup. The Earth sits at the centre. The moon, sun, planets and stars revolve around it, loosely. The planetary orbits aren't circles around the Earth directly. Instead, each planet moves along a small circle called an epicycle, which in turn moves around the larger cycle, the deferent, centred near but not quite on Earth. It's not only geocentrism, it's sort of fancy geocentrism. The model was mathematically robust. Ptolemy's genius was not in proposing a centred cosmos. That idea had been around since Aristotle, but in how he refined it to match what he actually observed. Retrograde motion, so when planets like Mars appeared to move backwards in the sky, had baffled thinkers. But Ptolemy's epicycles made it make sense. Sort of. Imagine you're on a Ferris wheel that's attached to a larger Ferris wheel, which first of all is amazing. The motion is going to get complex as both of them spin in turn and possibly in different directions. It's fun, and the maths is, well, surprisingly manageable. Ptolemy used chords, so this is in place of maybe sines. Trigonometry in its chordal infancy, before they'd cut the chord. He constructed a table of chords for angles up to 180 degrees, in steps of half a degree. Modern trig functions didn't exist yet, but Ptolemy worked around that by defining the chord as an angle theta in a circle of radius 60 units, such as the chord of theta is 2 times the radius times the sine of theta over 2, or rather, that is what we would call a chord in relation to sine. He just called it a chord, a line across a circle. So for radius equals 60, which was his choice, a chord of theta is 120 times sine theta over 2, if you are reconstructing this at home, which I'm sure you all are. These tables allowed for calculations of planetary positions with stunning precision for the time. If that feels like a lot, welcome to ancient astronomy. It was like trying to predict tomorrow's weather with an abacus and a goat's shadow. Let's zoom in on his trigonometric work. Ptolemy didn't invent trigonometry, but he expanded it significantly. He was the first to prove what we now call Ptolemy's theorem, which says, in a cyclic quadrilateral, so four-sided figure inscribed in a circle, the sum of the products of the two pairs of opposite sides equals the product of the diagonals. So mathematically, if we have a circle that is ABCD, with a quadrilateral drawn inside at ABCD, we could say that AC times BD is equal to AB times CD plus AD BC. The sum of the product of opposite sides is equal to the product of the diagonals. It's a mouthful, sure, but this theorem underpins his chord table. From it, Ptolemy could interpolate new chord values and calculate angle sums and differences without ever using the word sine, which frankly is a sin. If you want, you can go and look up his theorem. It really is quite beautiful, but you don't need to understand how it works to realise that he created a tool for calculating new trig values from old trig values. By his method, he only needed to measure a number from bits of string in a circle, and then he could evaluate the rest of this book from those few data points. Mathematicians are ingeniously lazy. He also constructed what amounts to an early version of the law of sines for spherical triangles, used to calculate celestial angles, similar to Menelaus's work. For context, Hipparchus had done some trig, but it was Ptolemy who turned it into a systematic tool, and later Islamic mathematicians who would refine and expand it, eventually flipping his chord table into sine tables because they are just so much more useful. When Ptolemy wasn't busy charting the skies, he was drawing the Earth. His work, Geographia, is the earliest known attempt at creating a grid-based coordinate system for mapping the known world. He listed over 8,000 locations, each with coordinates measured in degrees, and even addressed the curvature of his Earth in the calculations. Yes, you heard that right. Ptolemy believed the Earth was round. He just thought it wasn't going anywhere. The ancients got a lot wrong, but they did not believe the earth was flat. Let me say that again for the people at the back. Ancient mathematicians did not believe the earth was flat. Now, you might have noticed me saying he accounted for the curvature of his earth, and that's because his earth is not the same as our earth. His maps were wildly inaccurate by modern standards. So Africa was squished and fat at the bottom, India was tilted on its side, China was a bit of a suggestion, yet somehow connected to Antarctica and Africa, but the structure was innovative. He also tried to compute the Earth's size. He used estimates of the length of the equator and converted that into degrees. His values were flawed, but the method was geometrically sound. Can we talk about Columbus? So Chris, to his friends, tried to sail to China based on Ptolemy's calculations for the size of the world, and prepared for a journey accordingly. He even arrived at roughly the point that China should be, only it was the Americas, still half a world away. But if Ptolemy had got the calculations correct, then Chris might not even have attempted the journey, and the Americas might have been spared Europeans for another few hundred years. If only. Here's the key. While today's maps use the Mercator projection, Ptolemy tried several types, including conic and pseudo-cylindrical configurations. Personally, I think anyone who creates their own map is an idiot, but maybe I'm just projecting. Let's pause to appreciate Ptolemy's third act, optics. Just a little light reading. He investigated reflection, refraction, and vision itself, combining empirical observations with geometric theory. He used experiments involving light passing through air, water, and glass to approximate the angles of refraction. While he didn't discover Snell's law, because Snell wasn't born yet, Snell being another Latinization of the first discoverer, Ibn Sal. Okay, that's not quite true. They lived about 700 years apart, but it's tough to say who got there first, really. Where was I? While he didn't discover Snell's law, he is the first recorded mathematician to give a compelling account of the phenomenon. He also believed vision occurred because of rays sent out by the eye, not received by them. We now know that's wrong, but his use of rays as geometric lines was a conceptual leap towards later developments in geometric optics. You might say he had a real eye for detail. Now, let's address the elephant constellation in the heavens, astrology. Yes, Ptolemy did that too. In fact, he wrote a treatise on it, Tetrabiblos, 4 books, on the interpretation of celestial influence over earthly events. To Ptolemy, astrology wasn't just fortune-telling with rhinestones. He approached it as a serious inquiry into causality. The stars and planets didn't determine your fate, but they might nudge probabilities. Much like weather, certain configurations made certain outcomes more likely. He drew a firm line between astrology and superstition, even mocking practitioners who relied on omens or dreams. For Ptolemy, astrological influence operated through natural laws. He compared it to how the sun affects the seasons, or the moon affects tides, both physical, observable, and measurable. He emphasised natal astrology, so that's the interpretation of a person's birth chart, and claimed that environmental factors at birth could influence temperament, health, and behaviour. It's the closest antiquity came to writing personality profiles in the sky. Whether we agree or not, Tetrabiblos remains the most widely cited astrological text for centuries. It was translated, annotated, and cited by Arabic, Latin, and Renaissance thinkers alike. For better or worse, Ptolemy's astrology really made the rounds. Let's get back to the maths. You've heard the phrase the Ptolemaic system, and you've probably pictured nested circles, deferents, and little planetary loop-de-loops. But there's another ingredient, the equant. Now, this is where things get juicy, so bear with me. The equant is a point offset from the centre of a planetary's orbit, such that the centre of the epicycle moves at a constant angular speed with respect to it, not with respect to the Earth. I'm going to say that again, but a bit more slowly. because I think maybe we might lose the significance of this. So it's a point away from the centre of the planetary orbit, such that the centre of the epicycle moves at constant angular speed with respect to the equant and not the centre of the rotation. So here we're looking at centres of rotation and centres of speed as different things. This completely violates the Aristotelian rule that celestial motion must be uniform and centred on Earth. So why did Ptolemy include it? Well, because it worked. It let him match observed planetary positions much more accurately. Without it, the maths doesn't add up. The equant was his way of saying, look, I know this breaks the rules, but have you seen Mars? Here's a simplified breakdown. Let C be the centre of the deferent, E the equant point offset from C. The epicycle centre P moves along the deferent, and P's motion is uniform relative to E, not C. Just to clarify, we're saying the path is circular, but the speed is non-uniform. This subtle shift allowed the system to mimic non-uniform planetary speeds without giving up on circular motion. It's like saying, yes, I'm still dating geometry, but I'm cheating emotionally with calculus. It also set up the conflict that would eventually bring the whole system down when Copernicus, Kepler and Newton arrived on the scene. Their biggest complaint wasn't the geocentrism, it was the cheating. Ptolemy promised circular perfection and then introduced offset centres and speed hacks. But the mad thing about it is that the current understanding of orbits, so these are the elliptical orbits, relies on constant area swept, which necessitates non-constant linear velocity. I mean, the whole thing is just absurd. And I, as a serious professional mathematician, treat experts in astronomy with as much suspicion as I do my colleagues in astrology. But the point remains, Ptolemy was wrong, but his ideas were quite good. Ptolemy's work spread far and wide, but not immediately. After his death, it was preserved primarily through Greek manuscripts in Byzantium, then translated into Syriac and Arabic. During the Islamic Golden Age, scholars like al-Battani, al-Sufi and Ibn al-Haytham, aka al-Hazan, studied and critiqued his work. They improved his star catalogues, adjusted his geographical data, and refined his trigonometric methods. Still, they respected his approach and reused much of his framework. The Almagest was translated into Latin in the 12th century and became the go-to astronomical reference for European scholars. Thomas Aquinas, Roger Bacon, and later Copernicus all read him. Dante even references Ptolemy's model in the Divine Comedy, placing Earth at the centre of the celestial spheres. But the tide began to turn. Copernicus revived the heliocentric idea of Aristarchus, you'll remember from episode 23, and while his model was still filled with epicycles, it shifted the cosmic stage away from Earth. Kepler ditched circular orbits entirely and replaced them with ellipses, a bold move, but a smooth one. And Newton threw down the gravitational gauntlet and gave us a physics that made Ptolemy's loops look like outdated screensavers. Still, Ptolemy's model wasn't demolished overnight. It took centuries to replace, not because people were stubborn, but because it worked within observational limits. His maths didn't need to be philosophically correct to be pragmatically useful. Even his flaws remain instructive. The equant, while mathematically effective, violated a physical ideal. And that tension between utility and theory still plays out in science today. We often use models that aren't true, but are useful, like the Bohr model of an atom or the economic supply curves. Ptolemy reminds us that mathematical elegance and physical truth don't always align like planets in Pisces. His work also raises questions about scientific longevity. Why did his system last so long? Because he gave readers a full package: mathematical models, data, tables, geometric diagrams, and procedures. It was a toolbox, not a thesis. He offered instructions, not ideas. That made his work sticky. It stuck around. And while his astronomy was eventually superseded, his attitude, measuring, modelling, tabulating, remains central to science today. You might say that Ptolemy was wrong about the universe, but right about how to do science. So, where Ptolemy really stood apart from his predecessors was in synthesizing multiple disciplines. He wasn't just the maths guy or the astronomy guy, he was the spreadsheet guy. He saw science as a network of models, interlocking, imperfect, and deeply useful. He also wrote clearly, methodically, and thoroughly. His books were instruction manuals before the YouTube how-tos. So what do we make of Claudius Ptolemaeus? He lived in a world that was smaller, slower, and more celestial than ours. Yet he built systems that expanded human reach beyond borders, across oceans, and through the sky. He didn't discover much about the universe, but he gave us the tools to chart its dance. He didn't know the Earth moved, but he made it calculable. He didn't invent trigonometry, but he turned it into a navigational language that guided both maps and minds. And yes, he was wrong, but he was helpfully wrong. The kind of wrong that taught future generations how to be right. As I'm learning in this podcast, you really need to make 39 terrible episodes before you absolutely nail it on episode 40. In the end, Ptolemy reminds us of a central mathematical truth, that usefulness can sometimes outrun truthfulness. A good model is a ladder, eventually replaced, but essential to the climb. This has been the Mathematicians Podcast. I'm Benjamin Cornish, thanking you for staying on this long orbital tour. If you liked this episode, consider recommending it to a friend. If they say no, then consider stealing their phone and subscribing on their behalf to Spotify and YouTube. It really does help the show. If you want to stalk me on the internet, then you can find me on Blue Sky at mathematicians-pod, or you can wait for next week, where we will be going from great mathematician to greater than or equal to mathematician. Keeping it real and playing it natural, it's time for another step closer to symbolic algebra. It's Diophantus. Until then, goodbye. The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.